In this video, I'm going to be going through the 3 worked examples in the Copeland Engineering Studies, the Definitive Guide, Volume 2. So they're already drawn on the board, and we're going to go through them. So in this first question, we haven't had to calculate the reactions. All the forces have been given to us. Here, I have already taken the reactions. I'm assuming that you know how to do the reactions. This video is not for that. And then for question 10, the reaction here is pretty obvious. The vertical reactions, if we have 5.5 down, we're going to have 5.5 going up. That's required. I've calculated the moment couple for the cantilever, for the fixed cantilever, and I'll come back to that when we get to it. Okay, so what we're going to do is we're going to start off with, for each of these, we're going to draw the shear force diagrams and the bending moment diagrams. So I'm going to use the area method. That's the way that that's what I did professionally. I have other videos where I have worked out, and when I was at TAFE in uni, I did definitely know how to calculate the sum of the bending moment at a specific location just by showing without working out rather than a graphical solution. But I think the graphical solutions are really useful here. Now, typically, and this is a bit of a habit I can't really break anymore, I like to tell this as a story, as a ridiculous story. So I like to say that the shear force diagrams are a tale of just forces going up and down. So we started off by going up 5 kilonewtons, right? Once upon a time there was a beam, started off at 5 kilonewtons, and it went across 1 meter. Then something bad happened, and we dropped from the 5 kilonewtons, we went up, down 6. So where we were 5 up, now we've lost 6, and we're now 1 down from where we started. Then what happened is we kept on going. Oh, maybe I've made this scale a little bit too big. Anyway, we're going to deal with it. We went down another 6. Oh, now things were really starting to get worrying. So here we were, I'm going to write this actually instead as 5 kilonewtons. And then we went across. Now we've gone 5 minus 6 equals minus 1 kilonewton. And we went down another 6, so now we're at minus 7. But things got better. We had a reaction that pushed us up all the way up by 10. We went from minus 7 plus 10 took us to 3. Which the scale looks like about that. 3 kilonewtons. And then finally, remember we always have to start and end at 0. We went down 3, which brought us back to 0. So I think that's close enough to being at scale. What I'm going to do is I'm going to write the distances here. In this case, they're each pretty easy. 1 meter, 1 meter, 1 meter. Okay, I think that's what I used to do professionally. Okay, so now what we're going to do is we're going to calculate the bending moment. And what we're going to do is we're going to calculate the bending moment at each of these locations by calculating the area that we're going to shade in each time. So what we've got first is we've got this first section, and we're going to call this block A. We're going to colour in how much ink do we need to colour in this block. Well, it's 5 is the magnitude, and its area, its distance is 1. So 5 times 1 is going to be 5. So we can mark that in on our diagram. Now, because it's above the line, we're going to go above. So we're going to start at 0, and we're going to go up 5. I think that's going to be my maximum. Now, I'm trying to set my scale in my head to make it a reasonable scale, something that shows up well on the diagram and on the camera. And I've got all this space down below. I don't like to use that space too much because I have to sit in a chair to write there. But so what I've got here, this value at this location here, it's equal to 5 times 1 equals 5. 5 times 1 equals 5 kilonewton meters. Now, I'm going to make my prediction that it's going to be the maximum, because wherever we cross the axes is where we're going to have our maximums and minimums. Right? Wherever we cross our axes, we're going to have our maximums and minimums. So the next I'm going to have is this area here, which I'm going to call B. Now B is minus 1 times 1. So what I'm going to do is I'm going to take 5, it's a running total, I'm going to have 5 minus 1. So 5 is this previous value, and we're going to go down 1. Why is it minus 1? Because it's below the diagram. So 5 minus 1 equals 4 kilonewton meters. Okay. Now what I'm going to do is I've got this next block, C. C is 7 meters times 1. So I'm going to have 4. Here it was positive 4. 4 plus minus 7 equals minus 3. Okay, so here I have 4 plus brackets minus 7 equals minus 3 kilonewton meters. Now, why did we get a minus number? Because it's a cantilever. We have a part of our beam is sticking up past our reactions. When we have a cantilever, we're going to have negative bending moment. Now, this is important, and I'll talk about that briefly in a second. But the point is, what we're going to do is we're going to finish this off first. We have D, our area here, D, and D is 3 times 1. So minus 3 plus 3 times 1 equals 0. I really should have used that same method for all of these. I didn't, but I may be able to make a better effort of that next time. Now, what we do is we label this as positive and negative bending moments, right? So we can write just positive and negative. Now, sometimes you will actually see that drawn upside down. There's no real hard and fast rule for drawing positive and negative bending moment. I would say there's a convention, and certainly my workplace, we always draw it this way, but there's no real convention. Now, when I look at this loading situation, I can anticipate that if this is my beam, I can imagine it's going to look like that. In an exaggerated situation, those forces pushing down, these forces pushing up, my exaggerated beam is going to follow this pattern. Now, if you look, that pattern is the exact opposite of what we get here. That pattern is the exact opposite of what we get here. We get a hump here and a hump here and an inverse hump there. Now, why that matters is if this was a concrete beam, we would have to, so for steel beam, it doesn't really matter. For steel beam, just as long as you can deal with the biggest absolute value, that's all that matters. But for a concrete beam, it does really matter because what you're going to do is you're going to put steel in the beam. So if this is our concrete beam, now this isn't likely to come up, but I say this because I know there have been HSC questions where we've had to talk about, well, okay, how much shear reinforcement, how much stirrups will we put in here? Well, we're going to put a minimum amount of stirrups all the way through. We're going to put a minimum amount of stirrups all the way through, and that's our minimum. And then here and here, we're going to use more stirrups. So we might put in more stirrups in this area for the A block, and then for the C block, we're going to put in a little bit more even there. We're going to put in triple spacing. That might be how we, it depend, I mean, we don't know this specific situation. I don't know if that's visible with the chair in the way. And then, finally, there's also for the reinforcing steel, we're going to put more steel, because we only put steel in the areas of tension. This is saying that the area of tension is going to be on the bottom, plus means we put more steel on the bottom, which is what we normally do. So we're going to put a minimum amount of steel through, all the way through the beam, but then we're going to have more steel. We're going to show extra steel here, and we might even have a second row of steel at this location at the bottom, but we also have to put some steel at the top. So I'll just draw that again without the stirrups, because the stirrups usually aren't too critical. Concrete, they can be more critical. I was going to draw that in black anyway. Okay, so what we might do here is we'll put minimum steel all the way through on the bottom, and then we're going to put some steel here where we've got our maximum negative. We'll put that on the top, and we're going to put additional steel where we have our maximum members there. So that gives you an idea of why we care about pluses and minuses. I'm not going to go into that with all the other questions. I don't think, maybe I will, because that might not have even been on the camera, in which case it would be kind of embarrassing anyway. Okay, so we're going to do that again. I'm not going to do the colouring in, I'm just going to do the maths this time around. So what we can do is we can make a prediction before we get started and say, well, how is this thing going to bend? Well, the pattern of the bending this time around is going to be I should have actually asked beforehand. I should have said, what do you think the pattern of the bending is going to look like? The pattern of the bending is going to look something like that. Now, we're going to predict where our maximums and minimums are going to be, and as well when we do our shear force diagram. So first of all, this beam, once upon a time there was a beam that had a bad day. It went down 4 to start off with. So it went down 4, but it went across. Now all of these things are directly lined up. That's why I draw these green lines, so that everything is lined up. Just so that maybe I don't do a great job because I'm freehanding all of this. If I don't do a great job, you at least know what the intention is. So we went down 4, and then we went across 1 meter. So we're at 4 kilonewtons, and we've gone across 1 meter, which I'm going to write here, 1 meter. Then the beam, things picked up. The day went a little bit better. We went from -4 plus 6 gets us to 2 kilonewtons. Now, we had the day got even worse. We went up 6, we went back down 6. We're back where we started at -4 kilonewtons. Can't catch a break this beam, but okay. Now, hey, you know what? Things do pick up. So they've gone from -4 plus 11 equals 7. We go up and we're at 7 kilonewtons. 7 kilonewtons. Now I'm going to label this quickly. The distances, this is 1.5 meters, 1.5 meters, 1 meter. Okay, that's our shear force diagram. So we could imagine if we were doing our stirrup spacing, I said I wasn't going to do this, but this is the last time. I'm not going to do it for the cantilevers because we're not likely to get that sort of question. We would just put in minimum steel, minimum stirrups everywhere. And then here at the 7, that's where we need major steel. So we're going to put in some extra steel at this location. Extra stirrups there. Okay. I'm going to remove that and we'll worry about that again later. Okay, so now we're going to say where we're going to predict because we've crossed the axis 3 times, we should have 3 different turning points, right? We expect 3 maximum or minimum locations. So what we're going to do is we're going to start off at 0. And we're going to say, what is the area of this block? Well, the area of this block is 4 times 1. So what I've got is 0 plus, it's 0 plus -4 times 1 equals, now I drew that the wrong side because it's -4. I got a little bit too, and this here helps me to remember that it's the opposite. So if it's up here, it's down there. So we've got -4 here. So 0 plus -4 times 1 equals -4, and the unit is kilonewton meters. Okay, now what I have is, I've gone from -4 from this value, and then what I'm going to do is I'm going to add plus 2, now this is positive, so it's a positive 2, it doesn't need a sign change, times 1.3. Now 4, so 2 times 1.5 is 3. -4 plus 3 is still -1. -1 kilonewton meters. So that's going to stay there. Now, the next thing is we've got now -4 times 1.5. So I've gone from here. I'm actually going to write it above. I'm going to put both of these above here just so I don't cross over myself. I'm going to say plus 2 times 1.5 equals -1 kilonewton meters. And then at this location, we started at -1 kilonewton meter. We started at -1, and then what we did is we then added -4 times 1.5. Now normally I never show brackets like this, but because we've got a minus sign, I just want to make that really clear. So -4 times 1.5 is the same as -6. So what I have here is I've got -1 plus -6 is the same as -7. So what I'm going to do is I'm going to go down here to -7. -7. Now, from -7, how do I, well, I just did that without even adding the numbers. I just knew that I could get to 0. But what I've got is -7. So at this location, I've got -7 plus 7 times 1 meter equals 0. but I know that it has to be that. I know it has to equal that location. So what is the reinforcing going to look like in that location? I'll just write here. Now in this case, when we were figuring out our bending, we know our maximum bending here is going to be -7 kilonewton meters. That's our maximum. That's the value that we're going to call M max. So when we use our formulas, later on we'll use our formulas where we have the spinning stress equals M times Y divided by I. This is the value, that value, 7, is that value. Right? That's what we're going to use. Now in terms of stirrup spacing, we've done stirrup spacing in terms of reinforcing. If this is our beam, really, we actually don't need bottom steel. It's a very unusual situation to say that we wouldn't need, but just checking, does this diagram match this, the opposite? Yeah, it does. If we flip it and reverse it now, we don't know if this number goes above or below the line. And I said we had maximum and minimum points. The fact is that we have turning points, right? So we can predict that if we cross the line, our maximum and minimum is going to occur at one of these places we cross the line. So in terms of how much reinforcing, well, I would say we'd probably put in enough minimum steel. Now, because it's minus, it'd be top steel, which normally we always put steel on the bottom, but rarely we need steel where it's in tension, and this is where we've got our critical. And then I would add in extra steel at that location. You're unlikely to ever get a question like that, but you know, it doesn't hurt to include it. Now, I'm not going to include it on the photo that I'll put up for this. But that's relevant. Okay, now the next one we're going to talk about, so this is a fixed cantilever. Now in the HSC, the syllabus says we can only give you a question that has a pin and a roller or a fixed reaction. They're the only two setups we can use. A pin and a roller or a fixed reaction. That's all we can do. We can't do any other combinations. At uni, you can have multi-span beams, but we're not worrying about that. So when we have a fixed reaction, what we can see here is that we have some horizontal and vertical forces, but if we ignore this, what we'd have is a moment couple. Now we might remember we talked about moment couples in year 11. I really don't like teaching moment couples. I don't know why, I just don't. Anyway, so I try to make really good videos for things that I don't like, so I have made videos with moment couples, check them out. But what would that mean is we'd have this infinite spin happening. We'd have this, sometimes it looks a bit weird when I'm holding my markers like that. We'd have this infinite spin happening. So we need and we can see that spin, that infinite spin would be a clockwise spin. So we're going to need some sort of anti-clockwise moment to hold this thing in place. Now that anti-clockwise moment is at the fixed reaction, because fixed reactions can have both a horizontal, vertical, and a fixed reaction, right? So they can have a diagonal reaction and a moment reaction. I think I said the wrong thing. I said, anyway, we're going to move on. Okay, so our shear force diagram, pretty simple, is we're going to go up 5.5. Once upon a time there was a beam, the reaction was 5.5, so that's what we went up, 5.5. And then we went down 2, and that left us with 3.5. And then we went down finally 3.5, and that left us at 0. And that's our shear force diagram. As for our bending moment diagram, well, there's two ways we can approach this. One is we can say, once upon a time, there was a reaction, a moment reaction of 1.45, and then it went down by a certain amount. But I'm going to work the other way. I'm going to work back to this value. So what I'm going to do is, rather than by taking away, this would be, you know what, just to prove we can go both ways, we're going to say this is 1.5, and then this location is going to be, yeah, looks about right. It's going to be 1.45, minus 5.5 times 0.2. And that is going to equal okay, so 5.5, I'll make that point a little bit clearer, times 0.2. Oh, equals 1.1. I should have been able to figure that out. Because it's a fifth. It was 1.5. So if I have 1.45 minus 1.1, what am I going to have? Well, let's just type it in just to be sure. Minus 1.1 equals 0.35. Now, that happens to be exactly what this area is here. What we have here is if we're measuring in meters, right? I didn't write millimeters. I think it's not required to write millimeters. It is required to write meters, I think. That's just drawing practice, is we do everything in millimeters unless specified otherwise. Here we have, if we have 3, so it's 1/10 of a meter. So if we're going to work in meters, 1/10 of a meter times 3.5 equals 0.53. And that gives me that answer there, which brings us back to 0. So it doesn't matter which way we go, we're going to get the same value. In terms of reinforcing, right, well, let's think about how this would go. This is going to create that sort of bending, which means that we're going to have tension on the top, which means that our steel is going to be on the top, and we're going to have our... So I'll draw it. We're going to have our... we might put in steel for 0.35 all the way through, and then we'll put in extra steel, maybe there. We'll put in the extra steel. I don't know, it depends on the circumstance, the width of the beam, all those sorts of things. But that gives you a rough idea of how to solve these questions, and there's full calculations in the book. I didn't check them, but I've done this before, so I think they look right. Be embarrassing it if it's not. Anyway, that will do for this afternoon.